Okay, so let's get started today. One thing I do want to bring up about the last two remaining quizzes is their wording is a little, I don't want to say tricky because it's not really tricky, but you need to be very careful when you go through and read the quizzes. Um, the wording is very particular, so make sure you read through the last two quizzes very carefully. Okay. And what did we do yesterday? We did a little bit more of Stokes' theorem, or I guess we started Stokes' theorem. Um, the Zoom lectures, yeah. So this lecture and all of the other lectures are in the discussion board under the discussion module 7-8 Zoom recordings. So if you click there, you'll have links to all of the videos on YouTube. Yeah, so yesterday we started with Stokes' theorem. So again, just to go back over it, the idea is given some sort of surface with a boundary curve, the surface can be a piecewise surface, the boundary curve can be piecewise. The idea is that you can calculate the circulation of F around C either, with this work integral or with a surface integral of um, of curl, basically, of curl dot n, but of curl. So one thing that we have to be a little bit careful of is the counterclockwise circulation is what we're calculating, or what we should be calculating, but this is counterclockwise with respect to whatever normal vector that we choose. Now, the idea is that we want to choose kind of an outward normal vector. And if we do that, then, for all the shapes that we're going to be looking at, we're going to get a kind of natural counterclockwise orientation on the curve. So it's not a big thing to worry about, but it is something to kind of have in the back of your mind. So we checked that Stokes' theorem holds for a sphere of radius 3, or at least a hemisphere of radius 3. So we saw x squared plus y squared plus z squared equals 9, z is greater than or equal to 0. We went through, checked the left side of it. We found that we got negative 18 pi. Went through on the right side, and this is the new side, right? So we wanted to set up a surface integral. To do that, we parameterize the surface. In this case, it was in terms of phi and theta. Went through all of that process, and then the new thing was calculating the curl of the vector field. Now, this nabla here, we've seen it before, but this is del x, del y, del z, or del x, del y, del z. And we're taking the cross product of that with our vector field. And it's important at this point to keep your vector field in terms of x's and y's, or x, y, and z's. And then once you're done with this cross product, once you're done simplifying all of these partial derivatives, if there are any remaining x, y, and z terms, you can then substitute in your surface. Right. If you substitute in your surface kind of early, so you say, well, y is this and x is this, then if you try to take the partial derivative with respect to x or y, then you're kind of out of luck there. It won't really make a whole lot of sense. So just hold back a little bit, take the partial derivatives, and then you get this vector 0, 0, -2 in this case. Plug everything into the vector or into the surface integral, and go through and compute it. So, like I said, we're going to do 2 more examples today. The next one, we're going to take the vector field F to be x squared minus y for z x squared. And our surface is going to be my notes say quote unquote usual cone, but I don't really like that. I know what this means in my head, but this isn't very clear. What this means is kind of the 45 degree or pi over 4 cone. So meaning in this case, this is not how it would be given on like a module assessment or a quiz or something. It'd be given with a little bit more information. But the idea is that actually, pretty much that is the information that we could just give you. This pi over 4 is equal to phi kind of information. But the idea is that this cone is going to be the z is equal to r cone. Right, it kind of has a slope one. It's at pi over 4, 45 degrees, however you want to think about it. But this is the type of cone that we're looking at. If we're trying to graph this thing, if we go out, change the scale here. There we go. So our cone is going to have kind of a top that looks like this. That's actually really poorly drawn. I'm not proud of that. But it's gonna, wow. I don't like this scale. So we're just gonna draw this. Sorry, I really hated that X angle that I did there. Makes it look really distorted. But the idea is that this side, the side of this has slope 1. Height 2. And a radius 2 at the very top. Anyways, this is our cone. So the boundary of the cone this is a circle of radius 2, so you can say this is x squared plus y squared is equal to 4. Keep in mind that this is at height z equals 2, or you could just say that this is r equals 2 at z equal to 2. Okay, so we've written down some information here. But the goal of this problem is to find counterclockwise circulation using the surface integral. Part of Stokes' theorem. Right, so that's what we want to do. So just remind us, this is a surface integral. Let's go back up. Right, this is a surface integral of curl dot n d sigma, or a better way to write it. Oh, did we not do a better way to write it? I guess it's fine. Or if we want this in terms of kind of our region, once we parameterize S, this is going to be the curl of F dot N dA or du dv. Right, the idea is that some magnitudes get canceled out, and then we just have this. Sorry, this is not the n vector. This is Ru cross Rv. Right, so a lot of cross products in these integrals. So the next thing we need to do is parameterize our surface. We have R of blank blank is equal to x, y, z. And given this information, looking at this cone, maybe XYZ isn't the greatest thing because like we have kind of circles running around here. This cone, we know that Z is already equal to R. So a nice set of coordinate system, or a nice coordinate system for this might be cylindrical coordinates. But we have this substitution for R already. Or sorry, for Z. So if we're using cylindrical coordinates, then x is equal to r cosine of theta. Y is equal to r sine of theta. And z in this case is equal to r. We know that from our z bounds up here, this is 0 to 2. We know that r is also between 0 and 2. And so we need to figure out theta bounds, but this is a cone centered around the z-axis. So this should be 0 to 2 pi. Yeah, so why again does z equal r? So there are a few reasons why we could get z is equal to r. One, it could be given to you in the problem. But if it's not given to you in the problem, if it's given to you something like this, or if it's given to you in kind of an x squared plus y squared kind of manner, you can go through, you can figure out the angle of this, and you can use, I guess, this triangle. To figure out that z is equal to r at all these places, right? Because if this is angle is pi over 4, then you can go through and deduce this. Right, pi over 4 is when sine of this is equal to cosine of this, and that's how you get z is equal to r. But let's just say that z equals r is part of the information that we're getting. So we've parameterized this, and we write this in the order r comma theta. Next is, well, we can take the partial derivatives and go through and find the cross product, or we could find curl. Let's maybe do the partial derivatives and cross product. I feel like we've done this type of derivatives before. So let's take derivative with respect to r. We get cosine of theta, sine of theta, 1. Derivative with respect to theta. we get a negative r sine, r cosine, 0. And their cross products, again, we take 2, 3 minus 3, 2, which is a 0 minus r cosine. For the second component, we have a negative out in front. Then we take 1, 3 minus 3, 1. So a lot of negatives running around here. Then for the fourth component, or sorry, the third component, we get 1, 2 minus 2, 1, which I'm just going to simplify to an r, right? One of these directions we get an r cosine squared, the other one we get a negative negative r sine squared, and we can factor those out and simplify. So this is what we get for the cross product. All right, and back to the new stuff here. So this curl vector, right? We have pretty much everything done. We have our bounds for the surface integral. We have this cross product vector. Now we need curl. Del del x, del del y, del del z, crossed with, and we can scroll back up because I don't remember it. So a slightly more interesting vector field now, or this problem. X squared minus y, 4z, and x squared. Okay, copied that down, right? Yeah. Okay. So again, same sort of cross product. First component, we have a del del y of x squared minus del del z of 4z, the negative out in front, del del x of x squared minus, minus a del del z of x squared minus y. And in our third component, del del x of 4z minus del del y of x squared minus y. Right, so this is the curl vector. Let's simplify. We get a 0 minus 4 for those partial derivatives. So we get a negative 4 here. The second component, we have a 2x minus 0, but we have this negative out in front. So this will simplify to a negative 2x. Last component, 0 minus a negative 1, right? Because you only get the y term there. So this should be a positive 1. It's also what my notes say, so that's good. It's good to check back in with your notes. Anyway, so we get this vector for curl. And again, we've stuck with x, y, and z throughout this whole process. But at this point, this is when we want to substitute in our parameterization. Right, we've already done, we've taken all of our partial derivatives. We don't really need x, y, and z anymore. So we need x, which is our cosine. So this is the vector -4, -2, r cosine of theta, comma 1. And so now we can go through and set up our whole integral. So the circulation is this double integral from 0 to 2 pi, 0 to 2 of -4, -2 r cosine theta 1 dot product with, scroll up a little bit, negative r cosine, negative r sine, r. This is a dr d theta. So we're not going to go through this evaluation. Well, I'll take it one more step, right? I'll do the dot product, but you know, going past that, it's a little it'll take a little while. So let's go through this. -4 times r cosine of theta, you get a +4 r cosine of theta. Second component, you get a -2 r cosine times a -r sine. So you get a +2 r squared sine of theta cosine of theta. Last component, 1 times r. That's nice. Get just a plus r here. dr d theta. Right, so this is a, if you just look at it in terms of r, these are polynomials, not too bad. Once you get in terms of theta, you have this cosine theta, okay? You have this sine cosine theta. So my recommendation would be to break this up into two completely separate integrals, or group this one wherever you want it, this last term here, because for this term you need to do a u substitution, right? Pick u equal to sine. But for this term, if you do that, it gets a little tricky. So make sure you would break this up into two separate integrals, and then at the end of the day, you get a 4 pi for your answer. Okay. So are there any questions about this problem? All right. So that is example 1 on the day. And I think for the second example, I think what we'll do is kind of go through piece by piece, but I don't think I want to like go through all of this in a lecture style. So I think what I want to do is write up this problem. So example, use Stokes' theorem to compute the counterclockwise circulation, not using the, well, I guess in general, just do it. But you're going to find that you don't really want to use the line integral part of this. So let's write down our vector field. This is xz, xy, 3xz, c is the boundary curve of the plane 2x plus y plus z is equal to 2 in the first octant. Right, so this is in the positive x, positive y, positive z octant. So if we try to graph this, yeah, we can graph this. This isn't too bad, actually. Much easier than the cone. But I need to leave some room for my x-axis. Okay. So just looking at this plane, if we're looking kind of in the first octant, right, we can look at the points like 0, 0, 2, for instance, and graph these points. And then we're basically going to have a triangle as our boundary curve. So we say that 0, 0, 2 is going to be on our plane. 0, 2, 0 right here is also going to be on our plane. And then 1, 0, 0 is going to be on our plane. Right? So, or at least our this section of the plane. And then what we can do is draw these lines in the XY, XZ, and YZ planes. And so this, it's not a good color either. Triangle here, this is our surface. So you can either go through and figure out the counterclockwise circulation around this thing, which means you have to parameterize each of these three lines. It shouldn't be that difficult, but setting up these three different line integrals, it can take a little while. So we can either do that, or we can do the surface integral part, and we're going to do the surface integral part. One thing to notice here is our normal vector, right? Our normal vector here, reading through the plane, so a bit of review. We don't really have a cumulative final exam, but if we did, this would be good review for writing planes. A normal vector, 2, 1, 1, the coefficients of these terms, right? This is pointing somewhere out in this first quadrant here, or first octant. Right, but this normal vector is the exact normal vector that we would want to use to give a counterclockwise orientation. So I guess what's nice here is you can go through and compute the normal vector in the same way that we did up here. Find the two partial derivatives of your parameterization, take the cross product, or given this plane, write down the normal vector. So I guess also, like, why is the vector pointing out this way? Why is that the correct normal vector? If you guys remember the right-hand rule, kind of, I cross j is equal to k, that type of thing. If you take this vector, sorry, I don't want to take the two vectors because my vectors would be pointing kind of like this, and then I'm curling them and get a normal vector. What you kind of want to think of is your hand is curling, right? Your right hand is kind of curling in, right? Your right hand is kind of like curling in like this. Well, that's a counterclockwise motion. And so wherever your thumb is pointing, that's going to be your normal vector. So since this direction is counterclockwise, then our normal vector should be pointing out this way because that also follows the right-hand rule. So I guess this cut down a little bit of the work. Sorry, now I'm worried about like if this is the correct magnitude of the vector. And even if we do pick this as our n vector, you know, this first of all isn't a normal vector. And the other thing about it is if it was the unit vector, you know, if this was our actual n vector here, then we would need to still multiply by the magnitude of the cross product. So I guess we actually can't get away from that. Maybe we'll put it as an aside. Maybe we'll say but the point is we should get some scalar multiple of this. I'm just not super confident that we'll get this exact vector here. So that's something to keep in mind. But okay, so what I want you all to do, and I'll chime in here in like, you know, 5-minute intervals or something like that. Maybe 3 or 4-minute intervals. Right? We need to find R of UV, right, with bounds on U and V. We need to find RU cross RV. We need to find the curl vector in terms of our parameterization. And then once we do all that, you know, maybe we'll, I'll check in with this part and we'll write down the full integral. So I will set some sort of timer, give 3 or 4 minutes, and then I'll come back in and check on this parameterization. We'll give another 2 to 3 minutes for the cross product, and then another 2 to 3 minutes for this curl vector. And then after all that, we'll finish up. So I'm also going to pause the recording. Okay, so for the parameterization, we want to start out R of x, y, z, and use the information that we're given, which is this plane. And so the idea is we can solve for one of these variables. Personally, you know, I kind of like to solve for the z variable in this case. So x remains the same, y remains the same, but then you can solve for z is equal to 2 minus 2x minus y, right? Flip-flop this z and this 2, or, you know, just subtract this stuff over. Either way. But you get 2 minus 2x minus y. And this works out nicely. Kind of the shadow in the xy plane is this triangle, so that's okay. We have the x and y bounds, and we can just go to kind of the x and y axes here. Oh, that's not actually true. Let's pause for a second, right? This is an example that we haven't seen yet, and we probably won't see again. So, right, the shadow of this is, it's not a rectangle. Kind of what we've done so far is write these bounds for our surface as a rectangle, but in this case, we actually have this triangle here. So we would set up bounds kind of how we used to set up bounds for these regions. You pick y or x to integrate first and then figure out your bounds. So I think we stick to my notes here. My notes say let's integrate with respect to x first or y first. So we have a 0 for y and then a 2 minus 2x. And then the x interval, it's just going to be that 0 to 1. Right. So again, this is a great review problem in a normal semester. But this is a little different. We don't just have a rectangle, we have this different boundary or this different region. Okay. So if you wrote down 2, it's a bit trickier. This is a slightly different example. If you wrote down 2 minus 2x, awesome, great job. But I think at this point we can actually also move on to this cross product. I'll give it another minute. Give it about a minute or so to go through, and y'all can figure out the cross product if you haven't already. If not, keep moving on. Okay, so for the cross product, arrange these things a little bit. Right, we've chosen the variables Rx and Ry. Let's write out those partial derivatives. So for Rx, you get 1, 0, -2. For Ry, you get 0, 1, -1. And so for the cross product, right, first term is 0, -1 minus a -2. So you get a +2, which is a good sign for the 2, 1, 1 up above. Second term, you get a negative out in front, but you get a -1 times a 0 or minus a 0. So your pluses there. And for the third term, we get 1 minus 0. So in this case, in fact, we actually did get 2, 1, 1 back. Again, it wasn't always guaranteed that we were going to get that vector back. So it's good to check, but in this case, it looks like we did. Now, if you did one of the other variable sets, you need to be a little bit careful, but you may not get this vector back. You may get something slightly different. Okay. And for the curl vector, I think, yeah, I think we're going to slowly go through this one. So again, the idea is we have del x, del y, del z. That's the cross product with our vector field up above, xz, xy, 3xz. Depending on how you take cross products, go through this however you want. But for us, we're going to have, or at least for me, we're going to have del y of 3xz minus a del z of xy. Then a negative del x of 3xz minus a del z of xz and then for the third term, del x of xy minus a del y of xz. going through taking the partial derivatives. First component, you get a 0 minus 0. Second component, we have a 3z minus an x, put a negative out in front of that. So we get an x minus 3z. Third component, you get a y minus 0, so just a y. And the last thing here is you want to double check that you don't have any terms that you haven't substituted in. Well, z we said was 2 minus 2x minus y. Comma y, and bit of simplification. We get 0x. Sorry, we get a 7x plus 3y minus 6, comma y. And plugging this all back into a surface integral, we have 0 to 1, 0 to 2 minus 2x for our y bounds. 0, 7x plus 3y minus 6, comma y, dotted with 2, 1, 1, dy dx. And we'll do one more step again, just to do the dot product. First component gives us a 0, right? 0 times 2. Second and third components, we're multiplying by 1s, so we should just get a 7x plus 4y minus 6 dy dx. And if you go through, you compute this integral, you should get a -1. All right. So that was the last example for Stokes' theorem. Tomorrow, we'll go over the divergence theorem. There is, again, kind of one long example for it, one shorter example. We'll check them out. But other than that, we are essentially done with all of the material. What's tomorrow? Tomorrow's Wednesday. So Friday, we'll have review questions, anything you guys want to talk about. Again, focus on module 7-8 since that is our final exam. Bring those questions on Friday, but tomorrow we'll finish everything up. And remember, there's a quiz today, there's a quiz on Friday. I'll get the homework graded. And one other thing it was brought up is homework 10 resubmissions are due next Friday, so Friday of finals week. I pushed it back to that day because you all are already studying for the module assessment on Monday. It's kind of a natural time to do that, but I didn't want to put this extra thing that's due on Monday, so I pushed it back to the end of finals week, to whenever you guys have some time during next week to get it done. So I will see you all tomorrow.